Now let's finish.
Does the book have its own way of solving basics, redox? Yeah.
This is the method the book recommends. Okay?
Is there another way?
Oh yeah, there is another way. There's a whole other procedure that you can use where you're canceling OHs and waters instead of H plus and waters.
And the book shows that.
And it's complicated to do that because you have to keep both things, you have to keep track of both things at the same time.
And the book goes over that one.
Both of them have hydrogen, both of them have
Because both have hydrogen, both have oxygen, you're trying to worry about ratios. Okay? That's why this system is better, easier. Now, having done this, is there any more cancellation we can do?
Yes.
There is, isn't there?
Because there's 8.
We can get rid of these 8 waters. We can make that into 8 instead. Now we'll write our final balanced equation. Okay? So, 8 water plus 7 sulfide plus 2 permanganate goes to form 5 sulfurs plus 2 manganese sulfides plus 16 hydroxide ions. Let's verify again that we are in balance here. So we've got 16 hydrogens here, right? We've got 16 over there. That's good. We have how many oxygens on this side? 8 of them here. 8 more here, right? So 16. We got 16 oxygens here. 7 sulfur, 5, 6, 7 sulfur here, 2 manganese, we're balanced. How do the charges work out? Well, total charge on the right is 16 minus. On this side we have 7 times minus 2, which is 14 minus, 15, 16 minus. We're set.
Man, we're good.
Yep. Okay? So I hope it doesn't bug you that we treat this as if it were in an acidic solution, even though we know it's in a basic solution. We just tack on this last step at the end, replace H plus with H2O, and then add the same number of hydroxide on the other side. And the math works out beautifully because you can cancel all the extra waters that you make.
See, it didn't bug me. But then when you just said basically crushing my dream that this is not a reality, this is just a facade.
This is just a way to solve the problem.
Then it was all okay.
This set right here is not intended to reflect what actually exists in the flask. You don't really get what actually exists in the flask until you get down here.
But in an acidic
Means
solution?
justify the end.
Something like that.
But in the acidic solution, is that really what's happening?
In the acidic solution, that's a lot closer to what actually happens, yeah. Okay? All right. One more bit of information for you, and we'll be done with Chapter 4. And you'll have like 15 minutes to work on homework before you leave. So that's kind of slick. All right. So did you want me to sing or no?
Yes. Yes. Especially because we're recording it.
Oh gosh, I didn't think about that. Okay, here's my attempt. Ready? Ready for this? How will I know it's redox?
Keep going.
We're not laughing at you, we're laughing at this song. Because
No, you're laughing at me and it's fine.
No, really, it's counted.
No, that's all the lyrics I wrote. I'm sorry.
I didn't have time to get out my phone.
Well, you'll just have to watch it on YouTube, I guess.
he's putting these things on YouTube though, and he was recording.
Well, that's the only way Laura's going to be able to watch it. So, all right, let's answer. There are 5 things that you can look for. 5 things to look for to see that it might be redox. Number 1, If you ever see this listed, this ought to be just your initial, you should look at that and think, okay, this got to be redox. Okay?
Use redox to solve this.
Right, I think if it says that, then that's a really good clue.
Come on. What in the world is that? Okay. If it takes place in acidic or basic solution. So, if you're taking the AP chemistry exam and one of the problems says, the following reaction takes place in an acidic solution, your immediate knee-jerk Pavlovian response should be, wow, that's redox. Yeah, just like that. Just like that.
Just in the middle of the text.
Redox!
We get taken out.
And everybody else in the room will say, okay, she's on problem 6. Because you'll know the same thing.
Or really? I didn't know that. Now I'll pass.
Number 2. Sign number 2. Presence of a pure element.
Really?
Well, think about it. If you have a pure element on one side of the equation and you don't have it on the other side, what has to have happened to that element? Has to have been oxidized or reduced. Now, just because you see a pure element, that doesn't mean that you have to solve it via redox. I mean combustion. Combustion obviously involves oxygen. So yeah, combustion reactions technically are redox reactions, but you don't have to solve them this way. But if you see like sulfur becoming sulfide, especially if it happens to take place in an acidic or basic solution, bing, redox. Question number 3. High or low oxidation states. High or low oxidation states. And by high or low oxidation states, let's say maybe greater than or equal to +4, less than or equal to -4. If you see an oxidation state that high or that low, that's a lot of electrons to either have picked up or be doing without. Chances are that's going to move towards a different one. So, there are certain ions that you will learn are associated with this. One of them you've already learned today, permanganate. Permanganate ion is a prime candidate for reduction simply because it has manganese in the +7 oxidation state. That's huge. Chromate and dichromate for similar reasons. Good possibility there will be redox involved there. If you have something like perchlorate, just think about perchlorate ion. What's the oxidation state of chlorine in perchlorate? So perchlorate is what formula? ClO4 minus. What oxidation state is? +7. Chlorine is a +7? Probably some redox going to go on there. Okay? Now, this is not all, just because you have something in a high oxidation state, that doesn't always mean that it's redox. But if you combine it with these two, your chances are much better. Weaver.
What's the highest oxidation state you've ever seen?
7.
That's the highest.
Yeah.
It's not like +30.
Well, if you go above +7, you're talking about an entire valence shell.
Exactly.
That's a ridiculous amount of energy to have to overcome. 7's about as high or low as you would see. Okay, fourth thing that you could look for is if you have the same element in two different ions. And that includes, for example, the earlier case of bismuthate and bismuth, 3. That's bismuth in two different ions. If you have, say, manganese as manganese 2 and permanganate, two different ions, same element. If you're changing what it's attached to, you're almost certainly changing the oxidation state somehow. Okay? And then the last thing that I would have you look for is the same two elements present in different ratios. Okay?
Basically, you can't balance it easily.
Yeah. So for example, if you had an equation where you had NO2 on one side and N2O5 on the other, nitrogen has to have changed its oxidation state for that to work. That's going to be redox. Okay? So, I think I would probably look for them in this order as well. Usually the dead giveaway about redox is this first one. If it says acidic or basic solution, unless you can conclusively identify it as an acid-base problem, which we'll spend chapters 14 and 15 talking about how you do that, your first thought ought to be redox. If you have a pure element, you've got to be redox, although you may not have to use redox to solve it. High or low oxidation state, again, the tendency is going to be towards lowering that to something more manageable. Same element, two different ions, same two elements present in different ratios, talking about changes in oxidation states. Any questions? Congratulations, that's chapter 4.
Wait, you
Finally.
ask Laura if she has a question.
If she does, I'm sure she'll email it. Laura, if you have questions, email me.